There is a paradox in the universe that most of us encounter only through lines of text, charts, and dry sets of data. Humanity can reach extraordinary speeds, even approaching the speed of light. And yet that is still not enough to truly reach the stars. So what happens when speed is no longer the answer, and space itself becomes the question? The universe allows us to see remarkably far. It allows us to understand worlds that lie beyond our solar system, but it does not allow us to reach them through ordinary motion. Knowledge crosses distance more easily than matter does. Signals can travel. Human beings cannot. As more Earth-like worlds are discovered, this paradox becomes increasingly clear. Destinations exist, and they are not especially rare. But the paths that lead to them are incompatible with human lifespans, with history, and with the continuity of civilization itself. This paradox forces physics to ask a different question. Not how to move faster, but whether distance must be crossed through movement at all. And from that question, an idea begins to appear within the equations. An idea that does not involve traveling through space, but allowing space itself to move. If you are curious, stay with us, share your thoughts, and join us for these quiet journeys through the universe. And now, take a slow breath and prepare to enter the deeper layers of the story that lies ahead. We begin by noticing how distance behaves when measured not in miles or kilometers, but in time itself. When light leaves Earth, it moves at the fastest speed nature allows, covering a few 100,000 kilometers each second. Even so, its journey outward unfolds slowly against the architecture of interstellar space. Reaching the nearby Proxima Centauri system takes more than 4 years of uninterrupted travel, a span that already exceeds most human projects and plans. As that same light continues across the wider structure of the Milky Way, the scale shifts again. Crossing the galaxy from one side to the other would take on the order of 100,000 years, and in some directions, hundreds of thousands more. What appears immediate on planetary scales stretches into deep durations when placed against a galactic backdrop. Speed does not disappear, but its meaning changes, becoming modest rather than absolute. In this setting, the universe reveals a quiet constraint. The difficulty does not arise from imperfect technology or unfinished engineering. It emerges from the size of the space itself. Space-time is arranged in such a way that even the fastest signals require vast intervals to move between stars. The separation is not negotiable, and it does not compress in response to effort. Seen this way, cosmic distance becomes a structural condition rather than a temporary obstacle. Movement through space remains possible, but it unfolds within a framework where time accumulates naturally. This recognition does not demand urgency or frustration. It simply establishes the scale on which all further motion must occur, providing a steady backdrop for everything that follows. Human spacecraft have reached remarkable speeds by everyday standards. Probes launched from Earth now move faster than any object our species has built before, carrying instruments outward into interstellar space. Some of these machines have passed the outer boundary of the Sun's influence and continue onward, slowly drifting between stars. Yet, when their velocities are placed beside cosmic distance, the contrast becomes clear. Even at their fastest, such journeys would require many thousands of years to approach another stellar system. This is not due to a lack of ingenuity. It arises from a quiet mathematical balance that governs motion itself. Every conventional propulsion system depends on the same exchange: mass expelled backward to move forward. As velocity increases, the amount of fuel required grows disproportionately, not in a linear way, but in a compounding one. Carrying more fuel demands even more fuel to move it. And the cycle repeats. The equations that describe this process are indifferent to optimism or progress. They simply describe how momentum behaves in a universe that conserves energy. Across chemical rockets, ion drives, and even advanced concepts based on fusion. The pattern remains unchanged. Incremental improvements are possible and have been achieved, but none alter the underlying relationship. Pushing harder does not break the framework. It merely moves within it, step by careful step, always bounded by the same curve. Beyond propulsion limits lies a deeper boundary, one woven into the nature of motion itself. As an object accelerates closer to the speed of light, the energy required for each additional increase grows dramatically. From the outside, the object appears to resist further acceleration, as though inertia itself were intensifying. In physical terms, the object's effective mass increases with speed, demanding ever greater energy for diminishing returns. This behavior is not a technical flaw or an engineering inconvenience. It is a direct expression of how space-time responds to motion. The speed of light is not merely fast, it is a defining constant that shapes causality, energy, and time. Objects with mass cannot be accelerated past this limit through ordinary means. Not because engines fail, but because the structure of reality does not permit it. From within this framework, acceleration becomes a process of asymptotic approach. One can move closer and closer to the limit, but never arrive. Each gain costs more than the last, until the required energy grows beyond any finite supply. The universe does not forbid the attempt with force. It simply makes continuation increasingly impractical. As velocity increases, time itself begins to behave differently. Clocks moving at high speeds tick more slowly relative to those at rest. Lengths measured along the direction of motion become shorter. These effects are subtle at familiar speeds and profound near the speed of light. From the perspective of a fast-moving vessel, distances ahead appear compressed, and the passage of time on board stretches differently than it does elsewhere. In principle, this allows a traveler to cross great distances within a comparatively short personal duration. Years experienced aboard a spacecraft might correspond to centuries passing elsewhere. The mathematics permits this outcome, and physics confirms it through countless measurements. Yet the implication unfolds quietly. Such a journey, while feasible in theory, becomes disconnected from the society that launched it. A vessel returning after such a passage would arrive in a future far removed from its point of origin. Cultures would have changed, languages shifted, and histories unfolded without overlap. The traveler's timeline and the wider human timeline would no longer align. What was once a voyage outward becomes, by necessity, a one-way separation in time. When viewed collectively, these factors form a consistent picture. Distance resists compression. Propulsion scales unfavorably. Energy demands rise without bound. Time itself diverges between traveler and origin. None of these obstacles stand alone, and none arise from a single technological gap. Together, they describe a system in equilibrium, one that does not yield to linear solutions. Within this context, the challenge of reaching other stars appears not as a failure of effort, but as a consequence of how motion, energy, and space-time interlock. The universe sets conditions, and within those conditions, certain paths remain narrow. Increasing speed along a straight trajectory does not widen them. It shifts it when forward motion encounters structural limits. Attention naturally turns elsewhere, toward the medium itself. If traveling through space reaches an impasse, another possibility emerges, quieter and less intuitive. Considering whether space itself might participate in motion. At this point, the limits stand as they are, stable and well described. We remain alongside them, observing how consistently they appear across scales and theories. Before we look outward toward distant stars, let quietly observing its worlds and noticing how few of them can sustain a lasting human presence. We remain within a familiar neighborhood of space, orbiting a single star, where distance feels manageable and travel unfolds over months rather than years. From this vantage, the solar system appears rich with worlds, each following its own quiet path around the sun. At first glance, this variety invites curiosity. There are planets with thick atmospheres, barren surfaces, icy shells, and immense gravitational presence. Yet, as we observe them more closely, a different pattern begins to emerge, one shaped less by possibility and more by constraint. Among the rocky worlds closest to us, conditions diverge sharply from those that allow long-term stability. Venus, similar in size to Earth, is wrapped in a dense atmosphere that presses down with immense force, while surface temperatures remain high enough to soften rock. Its clouds circulate slowly, composed of corrosive compounds, reflecting sunlight yet trapping heat beneath. The planet turns at its own pace, indifferent to habitability, maintaining an environment that resists balance. Mars presents a quieter scene. Its surface stretches outward in cold deserts, shaped by dust and ancient riverbeds that hint at a different past. Today, its atmosphere is thin, offering little protection from radiation, and liquid water cannot remain exposed for long. Temperatures swing widely, and the planet's weak magnetic field leaves it open to the constant flow of particles from space. What remains is a world that preserves geological memory, but not the conditions required for sustained life at scale. Closer still, the Moon circles Earth in steady silence. Its surface bears the marks of countless impacts, unsoftened by air or weather. Without a substantial atmosphere or magnetic shield, it experiences extreme variations between light and shadow. Time there is measured in long days and nights, each lasting weeks. With no natural system to moderate the transition, it offers proximity and clarity, but little in the way of long-term shelter. Taken together, these nearby bodies illustrate a consistent theme. Relocation within the inner solar system does not resolve the deeper requirements of a stable civilization. Climate regulation, radiation shielding, liquid water, and long-term atmospheric balance do not arise easily. They are not features that can be assumed simply by changing location. The idea of moving outward, planet by planet, begins to lose its simplicity. Beyond the rocky worlds lie environments shaped by ice and immense gravity. Some moons orbiting the giant planets conceal subsurface oceans beneath thick shells of frozen water. These hidden seas remain of great scientific interest, offering insight into chemistry and planetary evolution. Their existence suggests that liquid water can persist in unexpected places, maintained by tidal forces rather than sunlight. Yet, these environments remain sealed beneath kilometers of ice, distant from the surface and difficult to access. The surrounding conditions are dominated by intense radiation belts and powerful gravitational fields. While such worlds may support study and exploration, their structure does not lend itself to open habitation. They are systems to observe, not places to settle. The gas giants themselves present a different scale of challenge. Composed primarily of dense atmospheres without solid surfaces, they offer no stable ground on which to build. Pressure increases rapidly with depth, and gravity shapes everything within their reach. These planets influence their surroundings profoundly, sculpting rings and moons, yet they do not provide a foundation for life as it is currently understood. What emerges is a narrowing of options. The solar system contains abundance, but not redundancy. Its worlds serve as laboratories, archives, and sources of material, but none replicate the balance found on Earth. Even where resources exist, maintaining large populations over long periods would require constant intervention, shielding, and support. The idea of reshaping a planet has been considered as a way to bridge this gap. Proposals to alter atmospheres, warm surfaces, or thicken air layers have been explored in theory, particularly for Mars. These concepts imagine gradual change unfolding over centuries or longer, requiring sustained energy input and infrastructure beyond present capabilities. Adjusting temperature alone would not be sufficient. Magnetic protection, atmospheric retention, and ecological development would also need to be established and maintained. Such projects operate on timescales that extend far beyond immediate planning. They resemble the largest constructions in human history, multiplied many times over, and applied not to structures, but to entire planetary systems. Even then, outcomes remain uncertain, dependent on countless variables interacting over long durations. As a result, transformation within the solar system appears slow by design. It favors patience over urgency, observation over immediacy. While gradual change may one day be possible, it does not offer a simple response to shorter horizons or emerging pressures. The solar system remains a place to explore and learn, but not easily to duplicate what already exists. Earth, viewed from this perspective, becomes an exception rather than a standard. Its position relative to the Sun allows water to remain liquid at the surface. Its atmosphere moderates temperature and supports complex chemistry. A magnetic field deflects much of the surrounding radiation, while a stable rotation provides regular cycles of light and darkness. These features align in a way that is not commonly repeated nearby. This balance is not absolute or permanent. It depends on systems that interact continuously, adjusting and responding over time. Earth carries a history of change within its layers and skies, and its present state reflects a particular moment within that history. Recognizing this does not diminish its value. It clarifies it. Holding these observations together, the solar system reveals itself as a place of origin rather than destination. It offers context, resources, and understanding, but limited alternatives for long-term continuity. The search for environments that resemble Earth or can support similar balance begins to look beyond this familiar region. Without urgency or finality, attention drifts outward, past the orbit of the outer planets, toward the surrounding stars. Around them, other worlds may circle, shaped by different conditions and histories. The question forms gently, not as a demand, but as a continuation of observation, carried forward into the wider galaxy. Before attention drifts toward unfamiliar technologies, we pause among the stars already known to us, noticing how many distant worlds appear inviting in theory, yet remain separated by distances that quietly resist ordinary motion. Over recent decades, the night sky has begun to feel more populated. Thousands of planets have been identified around other stars, their presence inferred through subtle shifts in starlight and rhythm. Some reveal themselves when they pass gently across the face of their star, dimming it by a small, regular amount. Others announce their existence through tiny gravitational pulls, causing their stars to sway almost imperceptibly. From these patterns, catalogs have grown, filling charts and maps with points that suggest variety rather than emptiness. Among these discoveries are planets that orbit within regions, often described as temperate, where starlight falls at a distance that could allow liquid water to persist on a surface. These zones are neither too close nor too far from their stars, and they appear around many types of suns. As observations accumulate, the idea emerges that environments resembling Earth's basic energy balance may not be rare. The universe, at least statistically, seems open to such arrangements. Yet even as this list expands, another measure asserts itself. Each promising dot on a chart is also a location in space, separated from Earth by years of light travel. The more worlds are identified, the clearer it becomes that availability is not the limiting factor. Destinations exist in abundance. Access does not. The nearest of these candidates orbits Proxima Centauri, a small star that lies just over 4 light-years away. Its planet, often referred to as Proxima b, moves close enough to its star that surface conditions could, under certain assumptions, allow liquid water. Its mass suggests a rocky composition, and its orbit places it within a familiar conceptual range. By astronomical standards, it is close. By human standards, it remains distant. Light itself takes more than 4 years to make the journey between these two stars. A physical craft, even one traveling far faster than any built so far, would require many thousands of years to cross the same gap. This remains true regardless of refinements to engines or materials. The separation is measured not only in space, but in time that extends well beyond individual lifespans and even beyond recorded history. There are additional uncertainties as well. Proxima Centauri is an active star, prone to frequent outbursts that release energetic radiation. Any planet nearby would experience this variability directly. Atmospheres may erode, and surface conditions could shift unpredictably. Even so, these details are secondary to the primary constraint. Whether ideal or hostile, the planet is simply far away. As attention moves outward, similar patterns repeat on larger scales. The TRAPPIST-1 system, located around 40 light-years from Earth, contains several rocky planets packed closely around a small, cool star. Some of these worlds receive energy comparable to that of Earth, and their arrangement suggests a compact, orderly system. From afar, it resembles a cluster of potential homes, arranged neatly within a single neighborhood. Farther still lies Kepler 452b, often compared to Earth due to its size and orbit. It circles a star similar to the Sun, but at a distance measured in well over 1,000 light-years. Signals traveling at light speed would take more than a millennium to arrive. Physical travel, under conventional propulsion, would extend far longer, spanning timescales that exceed the duration of entire civilizations. These systems can be studied with increasing precision. Instruments now allow rough assessments of atmospheric composition, temperature ranges, and orbital stability. In some cases, the presence of clouds or gases can be inferred. The planets feel almost within reach intellectually. They can be described, categorized, and compared. Yet this intimacy remains observational. The separation between knowing and reaching becomes more pronounced here. Telescopes compress distance into data, delivering information across space at the speed of light. Travel does not share this advantage. Matter moves differently than signals, constrained by inertia and energy. This difference creates a quiet divide. Worlds may be known long before they are ever approached. Communication illustrates this contrast clearly. A radio message sent toward a nearby star system could arrive within decades. A reply, if immediate, might return within a human lifetime. Exchange of information, in this sense, becomes feasible on historical timescales. The conversation could unfold slowly, but it could unfold. A vessel, however, would tell a different story. Even optimistic projections place physical journeys at durations stretching into many thousands or even millions of years. Such travel exceeds not only patience, but continuity. The connection between origin and destination dissolves over time, leaving no shared frame in which a single society might persist across the journey. This distinction reshapes how distance is felt. Space does not block awareness. It limits presence. Signals bridge stars easily compared to objects. The universe allows observation long before participation. In this way, distant planets resemble landscapes seen through clear glass, detailed and real, yet physically inaccessible. As more systems are added to the catalogs, the sense of contrast deepens. The cosmos appears rich with structure and variety, offering numerous environments shaped by different histories. At the same time, the means of reaching them remain unchanged. Conventional propulsion carries mass through space, step by step, bound by the same equations regardless of destination. This recurring pattern reinforces a single observation. The difficulty does not lie in finding places worth visiting. It lies in the method of travel itself, moving through space at finite speeds, even very high ones, does not align with the scales involved. The gap between stars persists, regardless of interest or intent. Holding this awareness gently, attention begins to shift. If the universe presents destinations without accessible paths, then perhaps the limitation is not location, but approach. The idea forms gradually, without urgency. Instead of asking how to move faster through space, another possibility comes into view. Whether space itself might behave differently, nothing is resolved here. The list of distant worlds remains open, continuing to grow with each observation. They circle their stars in quiet patterns, indifferent to who may be watching. And as they do, the question of movement lingers softly, carried forward, ready to unfold in a different direction. The Alcubierre model begins not with engines or acceleration, but with a quiet adjustment in how space-time itself is arranged. In the mid-1990 seconds, physicist Miguel Alcubierre explored a question that had lingered at the edges of general relativity. The equations describing space-time allow it to bend, stretch, and compress in response to energy and mass. Within those equations, Alcubierre noticed a particular configuration that did not resemble any familiar object or field, yet remained mathematically consistent. It described a region of space-time shaped in a deliberate way, forming what later came to be called a warp bubble. In this model, space behaves asymmetrically around a central region. Ahead of the bubble, space-time is compressed, bringing distant locations closer together. Behind it, space-time is expanded, allowing separation to increase again after passage. Inside the bubble itself, the geometry remains nearly flat. The ship enclosed within does not push against space or accelerate through it. It rests within a locally ordinary environment, while the surrounding space-time shifts around it. The distinction here is subtle but important. Nothing inside the bubble moves faster than light relative to its immediate surroundings. The ship remains stationary within its own pocket of space-time, obeying all local physical laws. From the perspective of distant observers, however, the bubble itself can move across space at an effective speed that exceeds light, not by breaking the limit, but by redefining the distance that must be crossed. This reframing marks a conceptual turning point. Previous approaches attempted to overcome cosmic distance by increasing speed along a path. The Alcubierre idea suggests that the path itself could be altered. Rather than crossing vast distances step by step, space-time could be shaped so that those distances are shortened in front and restored behind. From inside such a bubble, the experience would be unremarkable in physical terms. There would be no crushing acceleration, no intense inertial forces, and no dramatic relativistic effects acting on clocks or bodies. Time would pass much as it does in orbit around Earth. Systems would function normally, and the crew would remain synchronized with the broader flow of time experienced elsewhere. This feature addresses one of the persistent difficulties of near-light-speed travel. Traditional relativistic journeys separate travelers from their point of origin in time as well as space. A warp configuration avoids this divergence. The journey could, in principle, take days or weeks for both the travelers and those awaiting them, preserving continuity rather than breaking it. The bubble itself, however, would not pass unnoticed. From an external viewpoint, space-time distortion alters how light moves around it. Radiation approaching the front of the bubble would be compressed, shifting toward higher energies. Light trailing behind would stretch, shifting toward lower energies. Stars in the background would appear distorted, bent by the curved geometry through which their light must travel. These effects suggest that a warp bubble would carry a visible signature, not as an object moving through space, but as a region where space behaves differently. The surrounding universe would respond to this change, imprinting patterns in light and possibly in gravitational waves. The bubble would not be hidden. It would announce itself through the way it reshapes the paths of signals that pass nearby. Such considerations move the idea beyond abstract geometry. They imply consequences that could, at least in principle, be observed. Theoretical studies have explored how these signatures might appear, examining whether space-time distortions of this kind could be detected indirectly. These investigations remain speculative, but they anchor the concept within the broader language of physics rather than leaving it isolated as a mathematical curiosity. At the same time, the challenges become clear. Creating a warp bubble requires conditions unlike anything currently achievable. Alcubierre's original solution relies on regions of space-time with negative energy density, often referred to as exotic matter. This form of energy behaves differently from ordinary mass and energy, producing gravitational effects that repel rather than attract. In everyday physics, energy density is positive. Matter curves space-time inward, creating wells rather than hills. Negative energy density would invert this behavior, allowing space-time to be shaped in the precise way the warp solution requires. While certain quantum effects hint at small, localized instances where energy densities dip below classical expectations, no known process produces the sustained, macroscopic distributions needed for a warp bubble. Early estimates of the required energy were immense, comparable in scale to the mass energy of large planets. These figures underscored the gap between mathematical possibility and physical implementation. The equations permitted the configuration, but the resources they demanded placed it far beyond practical reach. Over time, refinements to the original model have explored ways to reduce these requirements. By adjusting the shape and thickness of the bubble, or by altering how space-time curvature is distributed. Later, studies have shown that the total energy needed could, in theory, be lowered by many orders of magnitude. Even so, the values remain far outside current capabilities, and the fundamental issue of negative energy persists. This tension defines the current status of the idea. Warp drive occupies a space between established theory and speculative extension. It is not forbidden by known laws, yet it depends on conditions not known to exist in usable form. It is neither a blueprint nor a contradiction, but a suggestion embedded within the mathematics of space-time. Within this context, the Alcubierre model serves a particular role. It demonstrates that the limits encountered by conventional motion are not absolute in every conceivable framework. The speed of light remains a local boundary, but the global structure of space-time admits a wider range of behavior than intuition alone might suggest. The idea does not promise arrival. It reframes the question. Instead of asking how to move faster, it asks how space responds to energy and geometry, and whether that response can be guided. This shift does not resolve the challenges of distance, but it opens a different direction of inquiry. As research continues, attention turns toward the smallest scales, where quantum effects subtly modify space-time. Experiments that measure tiny distortions, fluctuations, and forces provide glimpses into regimes where classical assumptions begin to soften. These measurements do not build warp bubbles, but they inform how space-time behaves under unusual conditions. For now, the Alcubierre drive remains an idea shaped by equations rather than engines. It rests within the language of general relativity, awaiting connections to phenomena that can be tested and observed. Its value lies not in immediate application, but in expanding the conceptual landscape. The universe remains vast, and the distances between stars do not shrink on their own. Yet within the fabric of space-time, patterns exist that suggest alternative ways of thinking about movement. These patterns do not hurry toward conclusion, they linger, inviting careful observation. As the exploration of space-time continues to unfold into quieter, more detailed questions, at a certain point, Our attention drifts away from vast distances and begins to rest on effects so small that they once seemed beyond reach, where even emptiness shows a measurable structure. When we speak about the quantum vacuum, we are not describing a void in the everyday sense. Even in regions stripped of particles and radiation, activity persists at a subtle level. Fields fluctuate, appearing and fading according to rules that rarely announce themselves. Most of the time, these fluctuations balance out, leaving no trace that can be isolated or guided. Yet, under carefully arranged conditions, that balance can shift in ways we are able to notice. We encounter this shift in what is known as the Casimir effect. When two uncharged metal plates are brought extremely close together, separated by a gap so small it approaches the limits of fabrication, the vacuum between them behaves differently from the vacuum outside. Certain quantum fluctuations fit easily in the open space beyond the plates, but are restricted within the narrow gap. This uneven allowance creates a slight pressure difference, and the plates experience a gentle attraction toward one another. What draws our attention here is not the force itself, which is very small, but what it reveals about energy. Between the plates, the vacuum contains less energy than the surrounding space. In relative terms, the energy density in that region is lower than the background level. Within physics, this difference is described as a localized region of negative energy density, not absolute or free-floating, but defined by geometry and scale. As we observe this, an important connection forms. The universe permits energy to dip below its average value in constrained settings. These regions are limited, delicate, and dependent on precise conditions, yet they are real and measurable. The Casimir effect does not rely on hypothetical substances or unobserved particles. It arises simply from shaping the boundaries within which the vacuum operates. In this way, a requirement that once appeared only in equations begins to acquire physical grounding. Negative energy, long treated as an abstract necessity in warp drive discussions, appears instead as a relative condition that can be engineered in small amounts. The quantities involved are minute, but the principle itself is present in nature. With this footing established, we find ourselves returning to space-time geometry. If energy distribution determines how space-time curves, then even subtle rearrangements of energy could, in principle, influence that curvature. Rather than asking how to push a craft forward, the question becomes how to arrange conditions so that space-time itself responds. This line of thought guided the work of physicist Harold White, who revisited the Alcubierre model with attention to structure rather than scale. Early warp drive solutions required energy comparable to entire planets, placing them firmly outside any practical consideration. White explored whether altering the shape of the warp bubble could change this requirement. Instead of a simple spherical boundary, he examined configurations resembling a torus, a ring surrounding the region of flat space-time. By allowing this boundary to vary over time rather than remain static, the distribution of curvature could be adjusted. Within the mathematics, these changes produced a striking result. The total energy requirement dropped by many orders of magnitude. In some optimized scenarios, the equivalent energy was reduced from planetary scales to values comparable to everyday masses. These numbers did not imply feasibility, but they changed the tone of the discussion. The problem shifted from being overwhelmingly impossible to being extremely constrained yet sensitive to design. Geometry emerged as a lever, capable of amplifying or reducing demands without altering the underlying laws. As we consider this, the importance of precision becomes clear. Space-time responds not only to how much energy is present, but to how that energy is arranged. Small changes in shape can lead to large differences in outcome. This insight reframes the challenge from one of sheer quantity to one of careful control. The movement from theory toward experiment unfolded quietly. While studying Casimir-based systems for spacecraft technologies unrelated to warp travel, White's team encountered signals that suggested extremely small distortions of spacetime. These effects appeared at nanometer scales and matched the geometric signatures predicted by certain warp-like configurations. The experimental setup was modest in intent. It did not aim to produce thrust or motion. It focused on measuring how specific arrangements of plates and fields influenced the surrounding vacuum. Over repeated trials, consistent patterns emerged, distinguishable from noise and instrumental artifacts. The distortions were minute, but their form aligned with theoretical expectations. What we see here is not a vehicle, but a shape. A warp bubble reduced to its smallest expression appears as a geometric feature, detectable only through careful measurement. It does not carry objects or shorten journeys, yet it confirms that space-time can respond in the way the equations suggest, even under laboratory conditions. This is where the idea of a nanoscale warp bubble takes on meaning. It is not a miniature version of interstellar travel, but a proof of principle. The geometry exists, the response is real, and the physics behaves consistently across theory and experiment. The scale remains tiny, but the connection is established. Scaling this effect upward remains the central challenge. The Casimir force diminishes rapidly as distances increase. Effects that are measurable across nanometers fade quickly at larger separations. Extending these phenomena to macroscopic dimensions would require extraordinary precision, maintaining boundary conditions across volumes far larger than anything currently achievable. We encounter here a familiar pattern in technological history. Many advances began as fragile effects observable only under extreme constraints, later refined through progress in materials and control. In this case, however, the demands are particularly exacting. Quantum behavior and large-scale structure would need to coexist without disrupting one another. Proposals to address this gap often point toward advanced materials designed to guide electromagnetic fields with unusual accuracy. Metamaterials, engineered to shape waves and forces in unconventional ways, represent one avenue of exploration. Quantum control techniques, capable of maintaining coherence and alignment at fine scales, represent another. None of these approaches offer immediate solutions, but together they outline a direction rather than a wall. As we hold these ideas together, a shift in perspective becomes apparent. Warp drive no longer appears solely as an imaginative construct detached from observation. It becomes a layered problem, anchored at one end in measured quantum effects and extending at the other into speculative geometry. Each layer connects to known physics, even as the complete structure remains unfinished. The distance between a nanometer-scale distortion and a vessel-scale warp bubble is immense, yet the path between them is no longer undefined. It is marked by challenges of scaling, stability, and control, rather than by missing principles or contradictions. We do not arrive at certainty here, and none is required. The experiments do not promise motion, and the models do not demand belief. They offer continuity, showing how ideas move gradually from equations to measurements, from abstraction to instrumentation, without abrupt transitions. As we linger with these observations, the quantum vacuum begins to feel less like emptiness and more like a responsive medium. It reacts to boundaries, to arrangement, to geometry. Within that responsiveness lies a quiet suggestion. Space-time is not rigid, but shaped by conditions that can be explored carefully, one scale at a time. The question that remains does not ask when warp travel will occur. It asks how space-time responds as our ability to shape and measure it becomes more refined. That response unfolds slowly, through experiments rather than expectations. Continuing onward, open and unresolved. Across the development of warp ideas, attention gradually shifts away from a single solution and toward a broader landscape, where space-time itself can be shaped in multiple, carefully varied ways. each carrying its own consequences. After the Alcubierre model outlined a sharply defined warp bubble, further work began to question whether such abrupt boundaries were necessary. In 2002, José Natario introduced an alternative formulation in which spacetime deformation is distributed more smoothly. Instead of concentrating curvature into narrow edges, this approach allows the transition between flat and curved regions to unfold gradually, spreading the effect across a wider volume. This change alters the character of the geometry in a subtle but meaningful way. Sharp gradients in curvature tend to amplify extreme conditions, concentrating energy densities and making the structure more sensitive to disturbance. By contrast, a smoother distribution reduces these peaks, easing the intensity at any single point. The image is no longer one of sudden compression and expansion, but of a continuous flow in how space-time is arranged. From this perspective, stability becomes a central concern. Gradual curvature is less exposed to quantum-scale irregularities that can arise when space-time is forced into abrupt configurations. Although the total region affected by curvature grows larger, the local extremes soften. Energy requirements do not disappear, but they are redistributed, trading sharp intensity for broader extent. Here, we begin to see warp drive as a design space rather than a fixed structure. Different geometric choices prioritize different outcomes, whether that is reducing peak energy density, improving tolerance to fluctuations, or easing control requirements. No single model dominates. Instead, each variant occupies a position within a growing family of solutions. This diversification continues as researchers explore even more complex forms. Beyond spherical or toroidal bubbles, theoretical studies have examined warp geometries with twisted, helical, or braided characteristics. These configurations introduce rotational elements into space-time curvature, creating patterns that differ fundamentally from simple expansion and contraction. Such forms allow curvature to be distributed along paths that wind or interlace, rather than remaining symmetric around a central axis. In some cases, these arrangements may offer advantages for specific tasks, such as short-range repositioning within a star system, where control and stability matter more than raw transit speed. The geometry becomes task-dependent, shaped by intended use rather than abstract elegance. At this stage, warp research begins to resemble other mature technical fields, where multiple architectures coexist. Just as different aircraft designs serve different flight regimes, different warp geometries could, in principle, serve different modes of space-time manipulation. The presence of alternatives reflects refinement, not uncertainty. As these models multiply, another implication comes into view. Any sustained manipulation of space-time curvature is expected to interact with the surrounding universe. According to general relativity, changes in mass-energy distribution propagate outward as gravitational waves, carrying information about the source that produced them. Recent simulations have explored how moving warp geometries would imprint such signals. Studies carried out in the early 2020s modeled the gravitational waves generated by warp bubbles with different shapes, velocities, and acceleration profiles. The resulting patterns differ from those produced by familiar astrophysical sources such as merging black holes or neutron stars. Each configuration produces a distinct combination of frequencies, amplitudes, and polarizations. Together, these elements form recognizable signatures, unique to the geometry that created them. Researchers have proposed organizing these results into reference libraries, allowing observed data to be compared against predicted warp patterns. Through this lens, warp drive becomes something that could, in principle, be searched for rather than merely imagined. If a sufficiently strong event occurred nearby, its gravitational imprint might be detectable as an anomaly, distinct from known natural processes. We are not assuming such signals exist, only noting that space-time provides a channel through which they would announce themselves. So far, no such signatures have appeared in observational data. Detectors such as LIGO and Virgo have been operating for only a short span of time, listening primarily for intense, transient events. Their sensitivity is limited, and quieter or more distributed sources could remain hidden within background noise. This absence carries little weight by itself. Gravitational wave astronomy is still young, comparable to the earliest period of optical observation when only the brightest objects could be seen. Sensitivity improves incrementally, extending awareness into regions previously beyond reach. As instrumentation advances, detection thresholds lower, and new frequency ranges become accessible. Signals that are currently indistinguishable may eventually separate into identifiable forms. Within this expanding field of observation, warp-related signatures remain theoretical possibilities, neither confirmed nor excluded. Here, we are left with a picture that continues to open rather than close. Warp drive research now spans geometry, simulation, and observation, linking mathematical structure to measurable effects without forcing conclusions. Each layer adds resolution while preserving uncertainty. Attention naturally drifts toward what future measurements might reveal as listening grows more precise and sustained. Space-time continues to act not only as a background for motion, but as an active participant whose patterns can, in principle, be read. That reading unfolds slowly, shaped by patience and refinement, and it carries forward into whatever forms of motion may one day be understood. Across the wider universe, motion leaves marks, and even when the source is distant or unseen, space-time itself can carry a record of what has passed through it. When a warp bubble moves, the surrounding geometry does not return instantly to its prior state. Curvature shifts outward, spreading as a pattern of gravitational disturbance, not unlike ripples traveling across a surface long after the initial motion has ended. These disturbances are not sharp flashes. They are extended structures, unfolding gradually as space-time adjusts around the path that was taken. In this way, a warp event would not vanish once it ends. Its passage would be written into space-time as a traveling signature, expanding outward and thinning with distance, yet remaining coherent in form. If such an event occurred within a reachable range, and if instruments were sensitive enough, it could be distinguished from more familiar sources of gravitational waves. Here, we encounter a quiet change in strategy. Instead of waiting to develop warp technology independently, attention turns toward observation. The universe itself becomes a record, holding traces of activity that may have occurred elsewhere and earlier. Space-time is not only a medium to cross, but one that remembers. These signatures would differ from those produced by colliding black holes or merging neutron stars. Natural events tend to be brief and violent, generating bursts with characteristic frequency sweeps. Warp-related disturbances, by contrast, would reflect sustained geometric manipulation, producing patterns that evolve more smoothly and persist differently over time. If a single such pattern were identified, it would offer more than detection. Its structure could be analyzed, compared against theoretical models, and used to infer the geometry that produced it. From the shape of the wave, constraints on curvature, velocity, and energy distribution could be derived. The signal would function as a kind of footprint, pressed into space-time itself. This possibility extends beyond gravitational waves alone. A moving warp bubble would also interact with its local environment. Interstellar gas could be compressed or displaced, leaving behind shock structures. Electromagnetic radiation passing near the bubble would be shifted, bent, or redistributed. High-energy particles might show unexpected anisotropies along the bubble's path. Because of this, detection would not rely on a single channel. Gravitational observatories could provide an initial indication, prompting coordinated observation across radio, optical, and gamma-ray instruments. A genuine warp-related event would be expected to register across multiple domains, each contributing part of the overall picture. Such a layered approach reduces ambiguity. Natural phenomena can be complex, but they tend to follow known relationships across different forms of observation. A warp signature would likely present a distinct combination of effects, aligning in time and direction in ways that do not match conventional astrophysical sources. At this stage, we are not searching for certainty, only coherence. The goal is not to declare discovery, but to notice patterns that resist existing explanations. The universe has often revealed new physics through such mismatches, where observation and expectation fail to align perfectly. If a coherent signature were ever identified, analysis would not stop at recognition. Computational models could be used to work backward, adjusting hypothetical warp geometries until simulated signatures align with the observed data. In this way, the signal itself becomes a constraint, guiding theory rather than being passively received. This process has precedents. Throughout history, complex technologies have been understood through their remains or outputs long before their internal workings were fully replicated. In those cases, artifacts or effects provided enough structure to narrow possibilities, accelerating understanding that would otherwise have taken far longer. Applied here, such reverse inference would not deliver a complete design. It would offer boundaries. Certain configurations would be ruled out, others supported. Entire classes of objections could be set aside if the signal itself demonstrates that a given geometry can exist and propagate. This does not imply immediate construction or sudden capability. Understanding often advances unevenly, with insight arriving long before implementation. Still, even partial confirmation would reshape priorities, indicating which lines of research align with realities already present in the universe. Alongside this possibility come broader considerations. Observing advanced technology elsewhere would raise questions beyond physics alone. Decisions about interpretation, sharing of data, and coordination across institutions would shape how such knowledge is handled. These questions unfold gradually, influenced by precedent rather than urgency. What matters first is restraint. Detection does not compel action. It invites careful interpretation, extended verification, and collective reflection. The scale involved ensures that responses unfold over years rather than moments. Here, we remain in a listening posture. Instruments continue to gather data. Simulations continue to refine expectations, and theory continues to expand its range of what might be possible. Space-time carries whatever has occurred within it, indifferent to who may later learn to read its patterns. As this listening deepens, the universe becomes less like a silent expanse and more like a textured record. Motion, whether natural or engineered, leaves traces that persist long after the source has passed on. Not all traces will ever be noticed, but some may eventually stand out, waiting patiently within the background. We do not know what will be found, or whether anything will be found at all. What remains is the act of observation itself, sustained and unhurried, as attention stays open to patterns that may one day reveal how motion has already been achieved elsewhere, long before it is understood here. Inside a warp bubble, motion no longer feels like passage through a hostile environment, but like remaining within a familiar enclosure while the surrounding universe rearranges itself. The physical conditions envisioned within such a bubble differ markedly from those encountered in conventional interstellar travel. Temperature remains regulated. Radiation levels stay close to those experienced in near-Earth orbit, and high-energy particles that normally permeate interstellar space are diverted around the bubble's boundary. Dust grains, charged particles, and even shock fronts from energetic events would follow the curvature of space-time rather than striking the vessel directly. In effect, The craft occupies a region that remains locally ordinary, while extraordinary motion occurs elsewhere, from within. Life proceeds without constant exposure to cosmic hazards. Systems designed for long-duration spaceflight would still be required. But the relentless accumulation of radiation damage and micrometeoroid erosion is largely absent. The surrounding space-time absorbs these interactions, allowing the interior to resemble a stable orbital habitat rather than a vehicle crossing an unprotected void. This separation from the external environment, however, comes with its own constraints. The same space-time curvature that shields the vessel also interferes with communication. Electromagnetic signals attempting to cross the boundary may be blocked, distorted, or shifted beyond usable frequencies. Light approaching from ahead of the bubble is compressed to higher energies, while light from behind stretches toward lower energies, leaving external views dim or heavily altered. As a result, a vessel in warp would operate without real-time contact. Navigation relies on internal systems and trajectories calculated in advance. External observation becomes indirect, mediated by models rather than direct sensory input. The experience resembles traveling through a region where conventional reference points temporarily lose relevance. Here, we notice a parallel with other phases of spaceflight that already involve brief periods of isolation, such as atmospheric re-entry or deep space occultations. The difference lies in duration and completeness. During warp, the separation is total, and the crew must rely entirely on internal coherence rather than external confirmation. Compared with near light speed travel, the contrast becomes sharper. A conventional relativistic vessel requires prolonged acceleration and deceleration, exposing its occupants to sustained forces that press against physiological limits. Even modest fractions of light speed demand careful management of acceleration over years, followed by equally long periods of braking. The journey unfolds slowly, and the human body must adapt continuously. Warp motion removes this burden. Acceleration does not occur locally, and inertial forces remain minimal. Time inside the vessel stays synchronized with time elsewhere, avoiding the temporal separation that defines relativistic travel. A journey measured in weeks for those aboard also passes as weeks for those waiting behind. This alignment carries psychological significance. Long relativistic missions risk turning travel into a one-way departure from a shared timeline. Warp travel preserves continuity, allowing departure and arrival to remain part of the same historical moment. The sense of disconnection that accompanies extreme time dilation does not arise. Even so, living within a moving pocket of space-time introduces a different form of isolation. External cues vanish, and the surrounding universe becomes inaccessible during transit. For some individuals, this absence may provoke unease, not from danger, but from detachment. The crew occupies a stable environment that feels almost too ordinary given the distance being covered. In this respect, warp travel differs fundamentally from generation ships or long-term orbital habitats. It does not ask its occupants to build an entire life in transit. Instead, it compresses the journey while intensifying isolation over a shorter interval. Psychological preparation focuses on managing confinement and sensory deprivation rather than endurance across decades. Here, we see how training and design shift accordingly. Habitats emphasize rhythm, routine, and internal variation to counter monotony. Support systems focus on short-term intensity rather than lifelong adaptation. The challenge is not survival across generations, but coherence across a temporarily sealed experience. When set beside traditional interstellar concepts, this balance becomes clear. Warp travel exchanges prolonged hardship for brief detachment. It avoids the biological toll of sustained acceleration and the social consequences of extreme time dilation, while introducing a new requirement: the ability to remain grounded without external reference. Taken together, these conditions frame warp drive as more than a theoretical shortcut. They outline a mode of travel shaped around human limits as much as physical ones. The interior of the bubble becomes a space where ordinary life continues, even as extraordinary motion unfolds beyond perception. As attention lingers here, the focus naturally shifts back toward those attempting to translate such environments from theory into design. The question no longer centers solely on whether space-time can be shaped, but on how living systems adapt when it is. That question remains open, carried forward from the quiet interior of the bubble toward the places where planning and construction begin. Across Earth, research into warp ideas does not unfold in a single place or under a single name, but appears instead as a scattered pattern of laboratories, funding streams, and quiet investigations. Some visible, others only indirectly suggested. At NASA's Johnson Space Center, one of the earliest formal efforts took shape within a small research group known as the Advanced Propulsion Physics Laboratory, often referred to as EagleWorks. The setting itself was unassuming, a modest laboratory within a vast complex, better known for missions that rely on familiar physics. Inside, interferometers and carefully isolated instruments were assembled to look for extremely small distortions of space-time, guided by theoretical work that explored how warp fields might be optimized. Rather than attempting propulsion, the focus rested on measurement. Configurations inspired by Casimir geometries and controlled electromagnetic fields were tested to see whether space-time responded within detectable limits. Technical documents outlined how metrics derived from the Alcubierre framework could, in principle, leave signatures accessible to precision instruments. The work moved slowly, constrained by sensitivity and noise, but it marked a transition from abstract equations to physical apparatus. This presence within a national space agency carried symbolic weight. Warp drive had entered an official research environment, even if only at a preliminary level. Funding remained modest, and expectations were carefully framed. Yet the topic was treated as serious enough to warrant time, equipment, and peer discussion. In this sense, we can observe warp research crossing a threshold, from speculative margins into institutional space. Beyond what is publicly visible, the picture becomes less distinct. Government funding for advanced physics often passes through broad categories, described in language that emphasizes foundational research rather than specific applications. Within these categories, studies of space-time fields and unconventional propulsion may continue without detailed disclosure. Some results are published openly, others remain internal, shaped by review processes that balance transparency with caution. This creates a gray zone between open science and restricted investigation. The motivation is not always secrecy for its own sake, but uncertainty about implications. Any technology capable of altering how distance is navigated would carry strategic significance, and research that hints in that direction naturally attracts attention from defense-oriented institutions. The boundary between civilian exploration and national interest becomes difficult to draw with precision. Outside NASA, warp-related work has also continued through independent organizations. After leaving EagleWorks, Harold White became involved with a non-profit institute focused on advanced space concepts. There, analysis shifted toward detailed modeling of Casimir geometries and vacuum energy distributions, exploring whether nanoscale configurations could align with warp metrics predicted by theory. Public discussion of this work sometimes moved faster than the research itself. Headlines spoke of real warp bubbles, while technical papers described specific boundary conditions and numerical simulations. The gap between popular interpretation and cautious analysis became apparent, reminding observers that language can expand faster than results. Still, the underlying effort contributed to a growing ecosystem in which warp concepts were examined from multiple angles. Here, we begin to see a broader pattern. Warp research no longer resides within a single institution or discipline. It circulates among universities, non-profits, and government labs, each operating under different constraints. The exchange of ideas continues through conferences, preprints, and informal collaboration. Even as some details remain compartmentalized, in the private sector, interest appears in more indirect ways. Companies known for launch vehicles and space infrastructure do not announce warp programs. Yet their hiring patterns and research investments suggest curiosity about unconventional propulsion. Specialists in plasma physics, general relativity, and advanced materials are recruited for roles that are not always publicly described in detail. Facilities associated with commercial spaceflight host a range of projects, most of them focused on incremental improvements. Within that landscape, smaller teams may explore ideas that sit further from immediate application. These efforts are rarely advertised, partly because their outcomes are uncertain, and partly because explaining them clearly to investors or the public would be difficult. What emerges is not a single race, but a diffuse pursuit. Warp drive is investigated quietly, often under broader umbrellas such as space-time physics or advanced propulsion theory. Progress is uneven, marked by long periods of refinement rather than visible breakthroughs. As observers, we remain at some distance from these activities, piecing together the picture through published work, funding trends, and occasional statements. The overall impression is one of cautious engagement rather than urgency. Warp drive is treated as a possibility worth understanding, not a destination assumed to be near. This restraint shapes the current phase of exploration. Research continues at the edges of measurement and theory, grounded in existing physics while testing its limits. The question is not who will succeed first, but how understanding deepens over time as tools improve and models sharpen. From here, attention naturally turns toward the approaches being explored within these scattered efforts, the specific strategies favored by different groups, and how they reflect differing assumptions about what space-time may allow. That examination unfolds gradually, following the same measured pace that has defined the journey so far. Rather than converging on a single solution, warp research has gradually separated into several distinct lines of thought, each approaching the same physical barrier from a different angle, shaped by different assumptions about what space-time may allow. One path remains closest to the original proposal, building directly on the Alcubierre metric, later refined through the work of researchers such as Harold White. This approach focuses on geometry and vacuum structure. The central idea is to engineer regions of negative energy density using carefully designed Casimir cavities, then arrange that energy into optimized warp geometries by adjusting the thickness of the bubble wall, reshaping it into toroidal forms, or allowing it to oscillate rather than remain static. Theoretical energy requirements drop dramatically, from planet-scale equivalents to amounts measured in tens or hundreds of kilograms of mass energy equivalents. This line of work treats warp drive as a problem of refinement rather than reinvention. The underlying equations remain intact. While every adjustable parameter is pushed toward efficiency, the attraction is clarity. If this route succeeds, the resulting warp behavior would closely resemble what the mathematics already describes. The uncertainty lies elsewhere, in whether negative energy can ever be produced and controlled in sufficient quantity outside carefully constrained laboratory effects. Alongside this conservative refinement, a second approach explores a different physical medium. Instead of relying on engineered vacuum states, some proposals examine whether large-scale electromagnetic fields and plasma configurations could generate the required space-time curvature indirectly, inspired by smoother geometries such as the Notario model. These ideas envision plasma structures, arranged in toroidal or layered forms around a vessel, producing gradients of energy density that bend space-time without invoking exotic matter directly. The imagery here resembles fusion research more than vacuum engineering. Dense, magnetically confined plasma circulates in controlled patterns, its energy distribution shaped with extreme precision. In theory, such arrangements could create effective regions of negative energy at the level of fields. Even if all underlying components possess positive energy, this direction feels closer to existing technology, drawing on decades of work in plasma stability and electromagnetic confinement. Yet it introduces its own difficulties. Sustaining precise plasma configurations at macroscopic scales, without turbulence or collapse, remains a challenge that has not yet been resolved. A third line of thought steps even farther back, toward cosmology itself. Dark energy, the pervasive component associated with the accelerated expansion of the universe, exhibits properties that resemble what warp metrics require, particularly negative pressure. Instead of attempting to manufacture negative energy locally, this idea asks whether the same mechanism driving cosmic expansion could be concentrated or redirected on smaller scales. Here, speculation increases, because dark energy remains poorly understood. Its behavior is inferred from large-scale observations rather than direct measurement. Still, the appeal is obvious. If space-time already contains a field that naturally produces repulsive effects, then warp drive might involve coupling to an existing cosmic ingredient rather than inventing a new one. The risk is equally clear. Without a deeper understanding of dark energy's nature, this approach rests on foundations that are not yet firm. These three directions are not isolated. Increasingly, researchers explore hybrid concepts that combine elements from each. Optimized Alcubierre-style geometries may incorporate smoother Notario-like boundaries. Casimir-based vacuum manipulation might be supplemented by large-scale fields or plasma structures. Speculative dark energy coupling could remain a distant goal, while nearer-term designs focus on measurable effects. At this point, we begin to notice how central computation has become. The space of possible warp configurations is vast, far beyond what analytic solutions alone can explore. Supercomputer simulations now act as design environments, testing millions of parameter combinations, discarding unstable geometries, and identifying narrow regions where constraints appear least severe. Warp research starts to resemble pharmaceutical discovery or semiconductor design, where progress depends less on single insights and more on sustained numerical exploration. In such simulations, each run represents a hypothetical bubble, defined by thickness, velocity, energy source, and stability criteria. Most fail quickly. A few persist long enough to warrant closer examination. These survivors guide future theoretical work and, occasionally, suggest experiments small enough to attempt in the laboratory. What unites all three approaches is restraint. None claims proximity to practical application. All remain experimental and theoretical, shaped as much by what cannot yet be done as by what might be possible. The divergence of strategies reflects not disagreement, but adaptation. An attempt to explore every plausible opening in a landscape constrained by fundamental physics. As these paths continue in parallel, attention naturally shifts toward the foundations beneath them. Each relies, in different ways, on assumptions about quantum structure, vacuum behavior, and the fine-grained nature of space-time itself. Whether any of these routes can advance further depends not only on engineering, but on deeper insight into the fabric they seek to shape. At a certain point, familiar descriptions begin to thin out, and the ideas that once felt solid no longer explain what is being asked of space-time. Classical physics treats empty space as absence, a background where objects move and forces act, but nothing itself takes place. That picture works well for everyday motion and even for much of astronomy. Yet warp concepts press directly against its limits. To shape space-time itself, the emptiness between objects can no longer be treated as inert. In quantum theory, the vacuum is not still. Even in the absence of particles, fields fluctuate continuously, giving rise to brief appearances and disappearances that never fully settle. This restless background is not an anomaly but a baseline, and effects such as the Casimir force arise precisely because boundaries alter how these fluctuations can exist. Two closely spaced surfaces restrict certain modes of the vacuum, creating an imbalance that produces a measurable force. This shift in perspective matters deeply. Warp ideas do not rely on creating something from nothing, but on working with what is already present in the structure of space itself. The vacuum becomes a medium rather than a void, and its internal activity becomes a potential resource. Here, we begin to recognize that any attempt to bend space-time must account for this underlying quantum texture. As the scale of interest grows, so does complexity. Simulating space-time curvature together with quantum fields quickly exceeds the reach of classical computation. Each region of space carries countless interacting degrees of freedom, and when curvature is added, their relationships multiply rapidly. Tracking this behavior in detail becomes less a matter of better equations and more a matter of computational capability. This is where quantum computation enters the picture, not as a solution, but as a possible tool. Quantum systems naturally encode superposition and entanglement, the same features that define quantum fields. In principle, such machines could represent vacuum behavior more directly than classical simulations ever could, allowing patterns to emerge that would otherwise remain hidden. We are not there yet, but the connection is suggestive. The implication is subtle. Progress in warp research may depend as much on advances in computation as on advances in theory. Understanding how space-time responds at quantum scales could require letting quantum systems model one another, rather than forcing classical approximations to carry the load alone. Beyond the quantum vacuum lies an even broader mystery. Observations of distant galaxies reveal that cosmic expansion is accelerating, driven by something that does not clump or dilute in the usual way. This component, known as dark energy, behaves as a uniform pressure embedded throughout space-time. It acts gently yet persistently, shaping the universe over immense distances and times. Dark energy is not directly detected, only inferred from its effects, and its nature remains largely unknown. Still, its defining property, negative pressure, closely resembles what warp metrics require. The universe already contains a field that stretches space-time. The idea that this background influence might be redirected locally is speculative. But it highlights an important point. Warp concepts are not isolated inventions. They echo processes already at work on cosmic scales. Here, we find ourselves linking the smallest scales to the largest. Quantum fluctuations animate the vacuum at microscopic distances, while dark energy governs expansion across billions of light-years. Both suggest that space-time is active, structured, and responsive, not merely a passive arena. At the deepest level, even space-time's continuity comes into question. Many approaches to quantum gravity suggest that smooth geometry breaks down at extremely small scales. Lengths far smaller than atoms, often described by the Planck scale, may reveal a fabric composed of discrete elements, loops, or extended objects rather than a seamless surface. In these views, space-time resembles a woven structure. Threads intersect, knot, and sometimes form defects. Concepts such as cosmic strings, microscopic wormholes, or topological irregularities arise naturally in this picture. These features are not added by hand. They emerge from attempts to reconcile gravity with quantum principles. If such structure exists, it changes how warp ideas are framed. Instead of forcing curvature into an otherwise smooth expanse, it may be possible to work with irregularities already present, places where geometry is less rigid and energy requirements differ. This remains theoretical, but it points toward a different strategy, one that aligns warp concepts with the deepest questions about what space-time is made of. Throughout this exploration, a pattern repeats. Each time classical intuition reaches a boundary, a deeper layer appears beneath it. Quantum activity replaces emptiness. Cosmic pressure replaces static expansion. Microstructure replaces smoothness. Warp drive does not create these layers. It exposes them by demanding more than surface-level explanations. As these ideas settle, attention drifts away from immediate application and toward understanding itself. Warp concepts become a lens through which space-time is examined, rather than a device awaiting assembly. In that role, they guide inquiry gently, suggesting where established descriptions fall short and where new ones might begin to form. Nothing here resolves quickly. The questions raised extend far beyond propulsion, touching the foundations of physics itself. What remains is an expanding view, one that moves deeper rather than faster, following the fabric of space inward as much as outward, and allowing understanding to develop at its own measured pace. Some ideas remain distant not because they are forgotten, but because they ask for more than current tools can provide. And warp drive sits among those ideas, held in place by a set of practical barriers as steady as gravity. The first barrier is energy, not only in quantity but in form. Warp geometries require controlled gradients of curvature, and curvature responds to energy density. In theory, the needed distributions may involve negative energy regions, or effective equivalents produced through fields and vacuum structure. In practice, no method exists for generating and sustaining such conditions at macroscopic scale. Even if the required energy could be supplied, shaping it with the necessary precision introduces a second barrier: materials. Materials have limits that are only partly understood even in conventional high-energy environments. Strong electromagnetic fields, intense radiation, and extreme gradients can degrade structures, alter properties, and introduce instabilities. A warp configuration would place a vessel within a region where space-time itself is being engineered, and it remains unclear how any known material behaves under such circumstances. The question is not only strength, but reliability across time. Repeated cycles and unexpected fluctuations. Control forms the next barrier. A warp bubble, if it could be formed, would need to be shaped and maintained dynamically, responding to disturbances the way an aircraft responds to turbulence. Yet the bubble's very nature complicates observation. External light can be shifted, distorted, or blocked. Electromagnetic signals may fail to pass through the boundary. Navigation would depend on models, internal sensors, and predictive control, all while the surrounding environment remains partially hidden. Safety grows from all of these constraints at once. Avoiding collision at effective superluminal travel is not a matter of steering around visible hazards. Interstellar space contains dust, plasma, and occasional denser regions, and the manner in which a warp bubble interacts with that medium is still uncertain. Failures of stability, abrupt shifts in boundary conditions, or unexpected radiation signatures remain unresolved questions. The list is long, not because the idea is careless, but because the physics touches every layer of a vehicle's design. Alongside these technical barriers lies the quieter barrier of prioritization. Funding for warp-adjacent research remains small, often scattered across foundational physics budgets rather than concentrated into a single sustained effort. By contrast, historical programs that transformed capability within decades, such as Apollo or major wartime research initiatives, were defined by extraordinary concentration of resources, talent, and political focus. Warp research has not received that kind of attention. This difference shapes the timeline. Predictions measured in half-centuries or more are not solely reflections of difficulty. They also reflect the pace of incremental progress under limited support. The path would look different under a different global choice. Enormous investment could accelerate instrumentation, expand simulation capacity, and support long-running experimental programs. Even then, acceleration does not guarantee success, but it alters how quickly uncertainty can be reduced. Two broad outcomes remain possible. In one, warp drive is found to be physically achievable in some form, perhaps not identical to early metrics, but close enough to reshape practical travel. A stable bubble could be created, controlled, and scaled, allowing journeys to nearby stars to unfold within human timescales without the biological penalties of near-light acceleration. Distances that once meant generations would become routes measured in weeks or months. Nearby star systems could feel less like unreachable targets and more like extended regions of exploration. In the other outcome, deeper principles impose a final boundary. Constraints related to causality, quantum stability, or the fundamental structure of space-time may prevent any macroscopic warp configuration from existing. In that case, the pursuit still carries value. Attempting to build warp drive forces physics into regimes where classical intuition breaks down, encouraging new understanding of vacuum energy, quantum fields in curved spacetime, and cosmological components such as dark energy. Even a definitive no would arrive with knowledge gained along the way. This is part of why the effort matters. Some research is valuable not because it guarantees a device, but because it clarifies what the universe permits. The tools developed for warp investigations, precision interferometry, vacuum engineering, advanced simulation techniques, and field control strategies, can reshape other domains even if warp travel itself remains out of reach. If warp travel did become possible, the cultural and scientific consequences would be profound. Even without romantic exaggeration, a region of space spanning a few tens of light years contains many stars and a variety of worlds. Over time, those systems could become destinations of study, habitation, and industry. The notion of civilization would expand from a single planetary base to a distributed presence, with knowledge and culture carried across multiple environments. Such distribution changes resilience. A single catastrophic event on one world would no longer define the fate of an entire species. Scientific discovery would broaden through direct access to new planetary systems, new stellar environments, and new physical conditions. The practical horizon of exploration would widen from a solar neighborhood to a stellar neighborhood. Yet even this vision remains grounded in uncertainty. Warp drive is not a switch waiting to be flipped. It is a question posed to physics, answered slowly through measurement, theory, and patient revision. The value lies partly in the asking, in the willingness to press against limits and learn what they are made of. The image that lingers is simple. Repeated attempts to understand a boundary, sometimes finding that it yields, sometimes finding that it holds, and always finding that the act of testing leaves behind new tools, new models, and new clarity. The universe does not change its scale, and distances remain vast, but understanding continues to grow, one careful step at a time, carried forward into the next quiet question. As our exploration settles, a single theme remains clear. The challenge of reaching the stars is not defined by failure, but by structure, distance, energy, time, and space-time itself form a balanced system, one that does not yield easily to force or acceleration. Conventional travel moves within this framework, while ideas like warp geometry ask a quieter, deeper question about how that framework might be shaped rather than crossed. Along the way, we have seen how physics does not close doors abruptly. Instead, it offers gradients. Concepts begin as equations, find grounding in subtle quantum effects, and slowly move toward measurement and experiment. Nothing here promises arrival, and nothing demands belief. What emerges instead is continuity, a sense that understanding grows by listening carefully to what space-time allows, and what it gently resists. The universe remains vast, patient, and unhurried. Its distances do not shrink, but our ways of thinking continue to expand. Thank you for spending this time in quiet reflection, drifting through ideas that unfold slowly rather than conclude. As we continue together, we will keep exploring the surprises and hidden structures woven into the fabric of the cosmos, allowing its mysteries to reveal themselves at their own calm pace.